Greetings, dear mathematicians. I welcome you to this learning platform where we simplify mathematics. So today we shall look at some of the applications of calculus of variation. As we have got a good foundation of calculus of variation, let us look at some of the problems that can be solved by the concepts of calculus of variation. And among these, we shall be looking or using some of these important notations. One, we shall be using what we call the kinetic energy, which we shall be denoting as T. And as we all know, kinetic energy is same as a half mv squared, where m represents the mass, v represents the velocity of the body. Next, we shall be using the concept of potential energy. As we know, potential energy is same as m, where m represents mass, g represents acceleration due to gravity, and h will be the distance or the height. Then we shall be using total energy, which we shall be denoting by E, and total energy is same as T, which is the kinetic energy, then adding there V, which is the potential energy. Then we shall not forget about using what we call the Lagrange's function, and we shall be denoting the Lagrange's function as L, and this L will be same as getting the kinetic energy and subtracting the potential energy. Then the most important equation that we shall be using as we look at these various problems will be what we call the Lagrange's differential equation. This Lagrange's differential equation says that when you have del L del Qj minus d dt of del L del Qj dot is equal to 0, where this Q dot here will be representing dq dt, where this Qj will be what we call the independent variable. So basically, with all these ones here, we shall be able to look at some of the mechanics problems that can be solved. Let us now swim into some of the applications. And to begin with, we have what we call the simple pendulum motion. We shall consider a string of length L. We have a string of length L, where at the end of the string we are attaching a bomb of mass m. So we shall give this bomb here what we call a vertical displacement through a given angle, that is angle theta. Now we have angle theta, then the respective distances, that is the horizontal distance, which is x, and the vertical distance, which will be y. Now this theta here can be easily related with x, y, and l by using what we call the trig functions. Now when we use cos of theta, that is the adjacent of this angle is x, and the hypotenuse will be this length L. So we can relate x with L by using what we call cos of theta. So cos theta is x over L, which means that x will be same as L cos of theta. Similarly, we have sine of theta, which is opposite over hypotenuse. Opposite is y, and the hypotenuse is L. So sine theta is y over L, which means that y can be L sine of theta. Now we have x and we have y. Let us get dx dt. Dx dt, we shall simply use what we call x dot. When you differentiate x with respect to t, we shall differentiate this one normally with respect to theta, and it will be same as L times. L is not changing, but theta is will be changing. So it means we have L differentiate cos of theta, get negative sine of theta, then times, because we are differentiating this with respect to t, then we shall multiply by the theta dt. So how does this one come? This is same as simply having, if you have dx dt, it's simply having dx with respect to theta, then multiplying with the theta dt. So that is exactly what we have done. So this is same as negative L sine of theta, then the theta dt, which we can represent with theta dot, and this will be our x dot. Similarly, let us get y dot, which is the y dt. Differentiate this one normally with respect to theta, so it will be L differentiate sine of theta, get cos of theta, then times, because we are differentiating this function with respect to t, so it means we shall multiply by this theta dt. So in other words, we shall have L cos of theta, then theta dot. So we have got our y dot and our x dot. But how will these ones help us? Let us look at how to relate x dot, y dot with what we call the kinetic energy. So let us look at kinetic energy. We know that kinetic energy, which is denoted by T, is same as a half mv squared. We need to look at v squared. So what is v? We already know the mass is m, but we don't know v. V squared. How do we get v? We already know that where we have our bomb, at this given point here, this bomb here has got x and y coordinates. So at this given point, we can determine the position vector of this bomb at this given point. That is after the displacement. Now, from here, at that given point, we can obtain R. We can obtain R, which R is same as xi plus yj, because it is having both x and y components, which means that R is actually same as L cos of theta I plus y. Y we have seen that one is same as L sine of theta of j. So V is same as the R dt. We already know that V is same as the R dt. So it is same as differentiating this with respect to t, is same as differentiating this with respect to t, which we have seen that this one here is representing x. So this will be same as x dot I plus y dot j. So where x dot is this one and y dot is this one. We have seen how we get x dot and y dot when we differentiate x with respect to t and y with respect to t. Now from here, if I need v squared is same as v dot v, which is actually same as having x dot squared plus y dot squared. So I will simply use this expression here and say that t is same as a half mv squared, which is x dot squared plus y dot, which is squared. So that will be our t. But we have x dot and we have y dot. So we shall simply substitute that and have a half m into negative L sine of theta dot. The whole of this one here is squared plus y dot is L cos of theta dot. The whole of this will be squared. So let us try to simplify that. That is a half m into, when you have that one there, it will be same as L squared sine of squared theta, then theta dot squared plus L squared cos squared theta dot squared. Now from here, we can still simplify this further as m. We realize that L squared and theta dot squared are common, so we can simply factorize out L squared theta dot squared and have this as sine squared theta plus cos squared of theta, and this one will give us a half m L squared theta dot, which is squared. This one here is same as having 1, so our kinetic energy will be a half m L squared theta dot squared. Let us now look at what we call the potential energy. Now, we shall look at potential energy by simply referring back to our diagram. So, according to potential energy, it is mgh. So, our h that will be considered here will be this displacement, that is the horizontal displacement, which is x, and we have seen that x is L cos theta. Now, from the formula, we shall say V will be same as, because we are looking at the object acting against the gravitation force, so we shall have this as negative mg of x. Now from there, we already have our x as L cos of theta, meaning that our V will simply be negative m gl cos of theta. So we have t, which we can give it equation 1. We have v, which we can give it equation number 2. So let us look at the Lagrange's equation. From Lagrange's differential equation. So we shall have del L. Our independent variable for this case will be theta. So it means it will be del L del theta minus d dt of del L del theta dot, which is equal to 0. So that is what we are having now. So what will be our interest? Our interest will be to get del L del theta and to get del L del theta dot. But what is L? What is L? L is same as T minus V. That is what we began with. L is same as T minus V. So it means L will simply be a half m L squared theta dot squared minus m g L cos of theta, which we can have this as a half m L squared theta dot squared plus mg L cos of theta. That will be L. So from this L, we can now have del L del theta and del L del theta dot. Now we have our L, which is a half m L squared theta dot squared plus m g L cos of theta. Let us look at del L del theta. That is partial differentiation of L with respect to theta. This is theta dot, so this one will not have any effect. So this will be like a constant, so it will give us 0. When you differentiate this with respect to theta, it will be mg L. That those are constants. Differentiate cos of theta, get negative sine of theta. So this will give us negative mg L sine of theta. Next, let us look at del L del theta dot. Differentiate this with respect to theta dot. So this will be a constant. So we shall differentiate this. A half is a constant. M is constant. L squared is constant. When you differentiate theta dot squared, you will get 2 theta dot. And this will be same as m L squared then theta dot. So that is now what we have as del L del theta dot. Now let us substitute into Lagrange's equation. Lagrange's equation is this equation here. So we can give this one equation number 3. So from equation number 3, which is del L del theta minus d dt del L del theta dot equaling to 0, will now become, so we are saying from equation number 3, we shall have del L del theta, which is minus mg L sine of theta minus d dt of m L squared theta dot, which will give us 0. So this will be same as when we have to multiply through by this negative. This is mg L sine of theta plus, when you differentiate this, m is a constant, L squared is a constant, so times differentiate theta dot with respect to t. So this is d theta dt. So d theta dt differentiated again will be d2 theta dt squared, which will give us 0. So we can now say that ml squared, I can represent this with theta dot, that is second derivative will be equal to negative mg L sine of theta. So now simplifying this one further, we realize that m will cancel out, L squared will reduce to L, so we shall simply have L theta double dot, which is equal to negative g sine of theta. Therefore, L theta double dot will be equal to negative g sine of theta. This one here will be the required answer, which will be the equation of motion of the simple pendulum. Thank you for watching, and if you find this video helpful, please consider subscribing and don't forget to share and comment. Thank you so much. We meet in the next lecture.
Yeah.